Let ABCD is a rectangular glass slab of thickness T and refractive index mu. Let O be a point object at a depth dr from surface CD. O is the point object which is situated at a depth dr from the surface CD. That is, dr is the real depth of point object O. Light rays from O are refracted at first surface AB, where I and R respectively are angle of incidence and angle of refraction. Two light rays from the point object O, one goes along OP and falls normally on surface AB and goes straight. Another light ray which goes along OS and falls obliquely on surface AB, and after refraction it goes along the path SR. Here at point S, angle of incidence is I and angle of refraction is R. If we extend two refracted rays, OP and S are backward, they meet at point I1. So, I1 is the virtual image of object O due to refraction at first surface AB of the glass slab. Here, POS is also I and PI1S is R. Since the ray PO and the normal at point S on the surface AB are parallel to each other, so this angle POS is equal to I. And since I1P is parallel to the normal at point S, so angle PI1S is equal to angle R. These rays are refracted again at second surface CD and goes along PQ and RT. After refraction at the second surface CD, the ray OP goes straight along PQ since it falls normally on the surface CD, and the ray SR after refraction goes along RT. Here at point R, angle of incidence is equal to R and angle of refraction is equal to I. We know that a light rays after refracting through a parallel glass slabs emerges parallel with the incident ray. So OS is parallel to RT, and so RT makes angle I with the normal at surface CD. If we extend RT and PQ backward, they meet at I2. So I2 is the final image of object O. Let I2 is at a depth dA below the surface CD, which we call the apparent depth. Angle PI2R is equal to I, since RI2 and ASO is parallel to each other. Since both refracted rays PQ and RT reaches our eye, so point P and S and Q and R are very close to each other. That is, I and R are also very small. Two refracted rays from the second surface CD, that is PQ and RT, both reaches our eye, so they are very close to each other, which implies that point P and S are very close to each other and point Q and R also very close to each other. That is, angle I and angle R both are very small. So when angle I and R is very small, we can write sin I equal to I equal to tan I and sin R equal to R equal to tan R. Applying Snell's law at point S, we get sin I equals to mu sin R, or tan I equals to mu tan R. Since we can write sin I equals to tan I when I is very small. Now tan I is equal to PS by PO. tan I is equal to PS by PO and tan R is equal to PS by PI1, which gives us PO equals to PI1 by mu, or real depth dr, which is equal to QO equal to QP plus PO, and QP is equal to T. T is the thickness of the glass slab. So we have dr equals to T plus PI1 by mu. Applying Snell's law at point R, we get mu sin R equals to sin I. Since I and R very small, we can write mu tan R equals to tan I. Now tan R equals to QR by QI1, tan R equals to QR by QI1, and tan I equals to QR by QI2, or QI2 equals to QI1 by mu. Now QI1 is equal to QP plus PI1 by mu, and QP is equal to T, so we have QI2 equals to T plus PI1 by mu. So apparent depth of the object, that is depth of I2 below the surface BC, dA equals to QI2, which is T plus PI1 by mu. Normal shift delta D equals to dr minus dA, that is real depth minus apparent depth, and we put the values of dr and dA, we get delta D equals to T1 minus 1 by mu. This is the equation for normal shift of the object, that is the difference in depth between the object and the final image of the object. Normal shift delta D does not depend on actual depth dr of the object. It depends only on thickness T and refractive index of the material of the slab. In this equation, there is no term containing dr. So, if the object O is just below the surface of the glass slab, that is just below the surface AD, it would have been the same equation, that is delta D equals to T 1 minus 1 by mu.